Okay, folks, how's everyone doing? You're so close. Where is it? Too close, right? Everyone already checked out?
Yeah.
That's really good because we definitely don't have anything due, say Wednesday.
Yeah, no.
Yeah, we don't have a homework due on Wednesday, right? So everyone's okay with being checked out? Okay. So we have just finished basically the beginning of vorticity dynamics. I was gonna do ideal flow today, but I don't think I'm gonna do that. I think folks like examples, and so we're gonna break down some of the ways that we start problems, especially computationally today. And we're going to talk about something very strange called dimensionless numbers. Folks familiar with that? Okay, everyone knows dimensionless numbers? Okay, Reynolds numbers. It's in the code that you just learned. RE. Okay, so we'll talk about that and we'll walk through the process of looking at code and constructing it from anew. And then on Wednesday, we'll do the end of ideal of their vorticity dynamics and the start of ideal flow. And after that, you'll basically just be looking at sort of special cases, analytic special cases. Okay. Any questions? Okay. You'll notice there's very few slides, and that's on purpose. Hold on. We also have a new guest today. Say hi to William. All right. I'll try not to swear as cannot make any guarantees. All right. So what are we looking at here? Correct. Now what are you looking at?
Oh, it's not a solar flare.
A solar flare? It's so many Earths tall. Yeah, so I tried to download this. Twitter's really annoying because it won't let you like save as a video. So you have to basically screen video capture. But there is motion. These are stills. And what you're seeing here is actually, do you see the spinny buoy? The buoy? Okay, that's a technical term. Spinny buoy. So this spinny buoy is 13 Earths big. And it is a tornado on the surface of the sun. Now, some of you have done the homework, specifically looking at what happens to a particle that's relieved with not enough velocity to escape. And we found that that means that you have what on the after the surface of the sun? You have something on top of the surface? An atmosphere. Who found out how big it is? Okay. It's at least that big, right? So interestingly enough, there's the surface of the sun that we get all of our wonderful, yummy light from. And then there's this hot, tenuous gas above it. And we see something in the surface of the sun or the atmosphere of the sun that resembles something that you see in Kansas. Kansas? Kansas. You know what Kansas is?
Oh, yeah.
We're not, there we go. That's what I was looking for. So this is a tornado or a twister, and it's on the surface of the sun. And you may be thinking to yourself, huh? What? So people looked at this and they said, oh my gosh, there's a little cusp. It must be an alien that's sucking off the surface of the sun. No, that's false. Anytime someone says to you alien, you know that it's wrong. Yeah.
I heard that you take something like that, right? You don't believe.
So that's, you can take Azure 2300 and there's a whole lecture. I'll maybe even invite everyone to this lecture, which will be the second to last day, which isn't that aliens don't exist. Aliens absolutely exist. There's just zero chance that they visited, played with people's butts, built pyramids and left. Okay, that did not happen. And it's absolutely insane that people think it is. Anything that looks like a coincidence probably is a coincidence because there's lots of coincidences. What's the easiest way to build big, tall buildings? Like that. Yeah. Dun, dun, dun. That's good. I like that tinfoil. That's really good tinfoil. Okay, so in fact, this is not an alien spacecraft refueling. This is a twister or a tornado on the top of the surface of the sun. And the question you should be asking yourself, well, why the hell are we talking about this in a fluid dynamics class? And this will go to this idea of where are fluids applicable? Is this atmospheric motion, can I treat it like a fluid? And the answer is yes, it is a fluid. There's plasma inside of this fluid, but it's still a fluid. And it has the same types of vortices that we see in Kansas that we see on the surface here, probably for comparable reasons. And you say to yourself, well, that's very strange, because if I made this piece of chalk 13 times the size of the Earth, and I threw it, it would have totally different effects, right? It would, for example, gravitation would really start to be a problem, would drag into other things, right? The mass here would not just be the normal mass. If I scale it up and I start moving things around, you have all sorts of issues. And the problems we're going to look at today when we talk about dimensionless parameters is the idea that fluids can look similar at very different scales as long as different pieces of what's important are balanced. Does that make sense? You'll see this better in a few minutes. Okay. So you have a homework. You're doing this homework, right? That's a yes from Isabel. Anyone else doing this homework? That's for spring break?
Yeah.
Oh, that's funny because I made it due not for spring break. That's fine. Okay. I'll remember that next when I assign homework. So in fact, you have something after spring break that is more important.
Oh, appointment.
Yeah, we have another appointment. You can't escape them. It's almost like this class has requirements. They're soft requirements, they're loose requirements, but they're requirements. Okay. And so specifically here, you should start slacking these starting this week for setting up, not next week, because next week I don't want to talk to any of you. The week afterwards. Well, okay, some of you. Okay, not everyone. And we're going to talk about checking in, doing the second check-in. And what you want to think about in the second check-in is the progress you've made since your first check-in. You set goals. Did you achieve them? What are you doing to get close to them? Are you better or worse off than you were 5 weeks ago? It's like a midterm election, right? You're better off than when you first got elected, right? Okay, and if you're late on homework, you're right. Spring break is the best time to catch up on it. So in fact, that's what we're going to do at the beginning of this class and maybe the whole class, depending on how long it takes. We're going to talk about the process of doing the problems on computer. Okay. And finally, just because there's not a grade on it does not mean I don't notice it's not there. How does he do that? Oh my gosh. Well, it turns out you just see me, but I see all of you. Oh, deep, right? Okay, it's not that deep. Okay, so you've seen this before, but we got a new flavor. Okay, just like I brought some new gum today, and it was awful. I left it in the study room.
It was really bad.
It was bad. It was good for like 5 minutes.
I was talking to Reed.
Yeah. If I see new candy, I buy new candy. I am a sucker for candy, and I'll try all the new candy, especially if it's sour. This is bad, so don't try it.
I don't think sour gum it doesn't work because like you want gum in your mouth for a long time and then
You don't want sour in your mouth for a long time.
Yeah,
They're literally opposites.
not fun.
Oh, this didn't work out very well. How do I get rid of that? I can move this?
Yeah.
If I drag it?
Yeah.
Oh shit, motherfucker, let's go. All right. So let's do this the way that we've been doing it before. Okay. Reed, what's the name of this equation? And what does it mean? Very good. Okay, and what does the 0 mean on the right hand side?
Just means that you can't like.
Very good. Okay, and then what is this equation, Desiree? Exactly right. This is the Navier-Stokes equation. What is it describing conceptually? Right, conservation of momentum essentially. And what are these first 3 terms? What's that? Right, good. Right, how? What kind of change in pressure is this? Pressure force, it's exactly right. Specifically? Not gravitational potential energy, but gravitational forces, right? So remember, forces act on momentum and energies act on energy, right? Okay, that was less interesting. Heat and energy act on energy. And then all of these are forces that act on the momentum change, right? We all get that? What are these terms here? Jasmine? These ones here? What's the hint that we have? In what type of forces these are? Okay, when we see mu, we think viscosity, right? So these are going to be our viscosity. What's the other word? Forces. Yeah, viscosity forces. And these happen in two different ways. What are the effects on the fluid here? What do they do to the fluid? Different ways. Like, let's say if I have my Amazon package, I can do what? I can compress it, good. And I can also yeah, well, this is not quite shrinking it. This is like squishing, but it's side squishing, right? Okay. Good. So these are your viscous terms, and this is your pressure term, pressure gradient term, and your gravitational potential energy. Okay. Andrew, what's this term? What's this equation? There we go. Everyone's got that one now, right? Okay. And what are these first three terms here?
The first one is how energy is changing in space and time.
Okay.
Typically, it's thermal energy and the kinetic energy.
Good.
And then the third term is gravitational potential energy.
Gravitational potential. Very good. Okay. Giselle, what are those next two terms? No, you're playing with a handicap today. That's okay. You're playing with a handicap. This one? Is that the pressure? Is that what you're saying? Okay, so when we think about this one, we look at the orientation of the P's and the U's with respect to where the differential is. Right? So when we say pressure work, what do you mean by pressure work? Because there's definitely pressure there, and there's certainly pressure here. No harm in getting it wrong. Should have lots of harm. False. Okay, if the P is outside, it's P dV work. Is that what you meant? Okay, good. And then the second term? Yes, stress and another, so the hint here is the tau. So the tau and the mu, we know, are both related to what type of works and forces? Viscous, right. So these are viscous works. So there's your viscous work, and the analogy that we use for viscous work is, oh,
Is that one the one the thing moving on top? The machine moving the top of the water?
right, yeah, so I guess that's going to the second part of this question. Maybe we'll ask this question first. What do these do, Colin?
That one is. That one was the internal, that one's the kinetic, right? Those
Yeah,
are-
these change the internal energy, and these change the kinetic energy, right? But they're in these nice little parentheses. Okay, so what does this mean?
I don't know.
Kobe, you want to tap in?
I think how pressure changes in the bag.
Okay, what's the analogy? Right? That's this term. Pressure differential. Notice there's a P dx. There is an unbalanced pressure. I put a pressure on this side. There's zero pressure on this side. This is causing motion. Pressure differentials cause changes in the kinetic energy. That's different than if I change the size of the box. If I change the box itself, right, that's going to change the internal energy. Okay, and then what does this term do?
The shear.
This is the one where you're spraying your friend. Right? Smack the top of the water moves. Right? This one here is what? Anyone?
Friction.
Yeah, this is where you're warming your hands up. Right? There's a layer of oils that you're now pressing against one another. And you can see those oils. They literally take off the top layer of skin. Doesn't make it right. What's the last one? Anyone? Heat flow. We all get heat flow. All right, now there's a new equation. Right? New equation just dropped. Let's go. Banger pre-season spring break. All right, what is this equation here? Anyone? No, do not look in the book. Yeah, what does it mean? What am I saying? What was that? Good. That's correct. Spinny boys, right? So this is why we had at the beginning of class, we had a spinny boy. So this is spinny boy. Spinny boy, spinny boy. Right? So what do those mean? What's its first one mean? Sorry, I can make it taller next time.
Then I have vorticity changes over space and time.
Right. So here's your total derivative of this thing called vorticity. And the vorticity means
What is vorticity to throw us a things a lot?
that's correct. Oh, not that. Okay. Okay, and it's a vector. Okay. And so what does this term mean?
Yeah, sections of the vorticity.
That's correct. So this is the vorticity advected through the fluid. So as the fluid moves around, you have vortex lines that are being brought together or pulled apart. Right? That's changing the strength of the vorticity. Does that make sense? And you have another phenomenon here. What's this last phenomenon? Alex? Diffusion. How did you see it was diffusion?
Del squared.
Yeah. So notice here, I got a something and a del squared. Anytime I have a something and a del squared, it's probably a diffusion operator. Okay. So this is the hint. Right? I can solve this like a diffusion problem. And if, for example, you solved something recently, like an advective diffusive equation, that might be really helpful. Right? Everyone did that in the homework, right?
Yeah.
Don't look at me like that. Okay. So great. So this is the vorticity formalism, and it's predicated on a number of things. We can go over those again, but mostly the idea here is that you have a fluid. Let's imagine this room is a fluid, and as I move around in the fluid, it is like my body is pushing the fluid all around me, but it's continuous. I cannot just press into the fluid and make it disappear. If I press into the fluid here, it presses into the fluid in front of me and it connects. So fluid fills in the back of my head, in the back of my body. So there are contours, there are lines that cover the entire fluid and connect them all, right? So we've used a mathematical formalism called vorticity. And we've gotten from this thing here, complicated and scary, to this thing here, easy breezy, right? Anyone scared by that? We started here. Okay. We used del cross, which is this piece. And I del crossed this. I del crossed this equation, and it helped me get rid of a lot of this jibber jabber. Get rid of that. I realized that conservative forces here, when I del cross them, those are probably gonna work themselves out. I don't really care. And so with pressure forces. Pressure and conservative body forces, he's gonna balance each other. Okay, and there's math that you can see in the book that does that. And then this thing becomes mostly this thing, but I have to move some other stuff around. And you get a really fun equation. What? That doesn't make any sense to me, Mateo. That's okay. In practice, deriving this, not that important. Using it, understanding it, much more important. Okay. What does it actually say? It requires that we have something called a stream function to solve it. Right? What was the stream function? Not just like we had stream lines, but we have now a stream function. Yeah. Yes. Yeah. What did it say specifically? Do you remember? Okay. So if you're looking at 4.3, we wrote something that looks akin to this. Del dot rho u equals 0. Okay. And this is just that top equation there, but in steady form. So d rho dt is 0. Okay. So you'll notice right away that we've put a caveat on the work that we're doing, because I'm not going to allow density to change with time. Okay. Can I boil water with stream functions? Why not, Isabel? Yeah, but I'm just talking about the stream functions themselves. Yeah,
Because in order for something to boil, the density needs to change.
correct. In order for something to boil, the density needs to change, right? Because hot stuff goes up. Right? Hot stuff doesn't go up if the density doesn't change. If the density doesn't change, you can't boil the water. Okay, so the formalism that we're using right here, which requires stream functions, already is not going to work for boiling water. But we don't care. We're going to get to there. Okay. So the first part here, you have this. You can say something like this. Okay. And that would be the curl of a vector potential, which obviously satisfies this requirement, right? Why does it obviously satisfy that requirement?
The gradient of the curl of a vector is 0.
The gradient of the curl of any vector is 0. So this is a mathematical trick. Okay? We love tricks. Remember, chemistry, biology, that's just physics. Math, not science, just tricks. Okay? All right. Only thing that matters in life is physics. Everything else is derivative. Okay. So when you look at something like this, okay, you have this del cross, you have this thing that we need to conceptualize. Okay, and this is a vector potential. That's going to be your stream function. Okay. Or actually, no, sorry. This one here, I need to write it better. It's like that. And that is your stream function. Okay. For the purposes of what we're going to do, though, we want to understand how this is used, because I can now relate the velocity back to this thing stream function. Let's go backwards for a second here. In 2 dimensions, in XY coordinates, those look different enough, right? Okay. This gives us a way to relate our fluid flow in two dimensions, like this, right? Back to one function. So what is that very similar to? What is the point of doing vector potentials? Yeah. No, what, I mean, why would I want to do this? Why would I create a stream function? What's the benefit? The benefit here is that it's a field formalism. It's a field. It's a vector field, potential field. Heard these words before? They do not mean the things that we frolic in spring break. Okay. It means that the fluid is defined everywhere within the fluid. When you're gravitational potential energy, that potential is defined everywhere in the space. Similarly, the U and the V are defined everywhere in the fluid by a single formalism, a scalar function. Right? Make sense? Okay. So it's not even shown here. Right? Not anywhere in here. Hidden underneath the U. This is the beauty of mathematics. Underneath something that makes physical sense, velocity, I've created something that makes no sense if you think about it too hard. Okay? But it's the thing that in this specific circumstance, when you have an when you have a steady flow, right, that can only change in this way, now I can create something that helps us find the velocity. Okay? Because they're now related. So if I press on it from one side like this, the other side has to move out. And now I can connect that flow, pressing in this way, with streamlines that have to go this way, right? And I've just created 2 sets of circles. This is the mathematical conception of that, right? Math is a tool, math is fake. They're just fake numbers. They're all just symbols, garbage that we write. The physics is real. Because we know if we do this, we know what will happen. The fluid will move. And all we're trying to do is describe it. Okay? Everyone's super happy now, right? Cool. Did I say that? Yeah. Good. Let's go backwards one. Can everyone see the bottom one? Okay. So, no, you can't see it? Okay. All right, let's go to how we write this really quickly, and we'll talk about what this looks like. So this piece here, the omega dt, this piece here, remember that in the d omega dt, it really looks like that, right? There's a ddt, there's a steady part, and there's an advective part. And you'll notice that when you end up putting those in the right place, you have like a semi-advective term, or you have an advective term here, and you have a semi-advective term here, and they'll mix around. Okay. And what you end up with is what we wrote last time, which is this equation. I'm just going to write it again. Okay. So what the hell did I do? Yeah. That's okay. The XY here? Yeah, so these pieces here, what does this piece mean? It's right there, right? It's row U. And what is this piece here? Row V. Okay. So here I have a vector equation in 2 dimensions, which would be d omega x, d omega y, right? With all these pieces. And over here, I just have one equation. Oh, that's not scary. It's okay. Okay. We're using this piece here. What is this thing?
Diffusion of vorticity.
That is the diffusion of the vorticity. Yeah. So I want to write that? Yeah. And one last relationship. What is this also equal to in terms of the stream function? What's that? No, in terms of the stream function. This is the vorticity, right? We know this is true, but we constructed it because we used a stream function that was a curl, right? You see that?
This curl of a curl.
Yeah. So this would be 6.60, equation 6.60, which is relating. It's how you get your U and your size in the first place, right? I think there's a minus sign. It's like that. Okay. Okay. So what's the point of talking to you about all this? Well, we have these 4 equations. This middle one we learned to code, right? This bottom one, we learned to code? No. Yes? No. Raise your hand if you've done it. Raise your hand if you've started it. Raise your hand if you knew that we were supposed to look at it. Okay, good. All right. You do. So again, that's this problem here. 610. Only one. Due Wednesday. Everyone knows that now. Okay. So here's incompressible flows in a rectangular domain. Essentially saying that if we know the stream function, we can get the velocities. We showed that. And we can define the whole flow with just this. Now that takes into account what assumption did I make at the very beginning in order to use streamlines?
Steady.
What is steady about it? The density is steady, right? Because the flow doesn't have to be steady, but the density has to be steady, right? Okay. Because essentially what we're looking at when we look at an equation like this is that we have to make some simplifications. So if we note up here, there's a lot of variables. Let's say I make a grid. Okay. And This is a very, very complex grid, okay? Relax, okay. So what are the properties that can exist at this point right here? Density, very good. Velocity, in which directions? Good, so let's call that U. And V. That it? Vorticity, okay, so that'll be a curl of these things, so it's not an independent variable. Let's put it in there.
Viscosity, you know?
Yeah, so that's a question. I'm gonna put viscosity, but I'm gonna put it in I'm gonna put it in question marks because we don't want it to change too much. Pressure. Remember, pressures make the world go round, they're up there. Anytime you see P, or anytime you see rho, temperature, okay, good. Is that it? Is that it?
Energy,
What kind of energy?
thermal energy.
Thermal energy, so that's inside of my T.
Gravity.
Do I have to mark that as a variable here? Is that a property of the fluid? Yeah. Because that's really like a height thing. If I go up higher, I gain gravitational potential. Right? If I go lower, I lose it, right? So you just have to orient it with respect to your bonds. So it's a good idea, but we won't need it here. Yeah. Kinetic energy is just the product of these, right? With themselves. Only one term that I missed. How do I boil the water? Heat flow. Okay. Does that make sense?
What's the difference between T and Q?
Ah, that's a very good question. What is the difference between T and Q?
Q is the current temperature that it's at, and T flow is how it's gonna change.
Right, so T is the flow's temperature at a specific location. And Q is the boundary passing through heat. Right, we think about like a large sack that we're warming up for some reason. Okay. That makes sense? So now you see the problem. Rho, U, V, maybe omega, we're not really going to count that as an independent variable. P, T, Q. Okay, this is probably a boundary condition. So this one's not so bad. This one is derivative of something else, not so bad. This might depend on the flow. That's going to suck. Right? But I have 1, 2, 3, 4, 5 equations. Okay, this will give me 1. This will give me 2. I might be able to relate these things to one another. For example, pressure and density. There's a constitutive relationship, right? But you could make some assumptions about it, right? We've said words like barotropic and baroclinic. So we need to know how P is related to density. Is there a T in there? Is it an ideal gas? Is it an adiabatic gas, etc.? Right? That's going to give you another equation. So that's 1, 2, 3, 4. You're still screwed, right? Unless T can fall out. If the pressure only depends on the density, and I don't have to care about that, then it's 4 and 4, and I'm done. Right? And I can start to solve the problem. If, however, the viscosity changes with time and space, you're screwed again. Right? So what's the other assumption we're making when we talk about this in the context of our computer? Let's assume a constant viscosity for the fluid, both in time and space, and it's not going to depend on things like temperatures or pressures or anything else. So we'll say, okay, that is a variable that we'll certainly use later, but we're going to ignore it for now. We'll start with the most bare bones model and we'll build up from what works. Okay. Okay, so currently this will depend only on that. Later on, when you want to boil water, it'll obviously depend on that, and you'll need that. Right? C'est bon? Okay. Okay, so we were talking about how we're constructing this one here, and we're just using these pieces. So what I want to talk about when we go through the process of, say, doing an example or turning this into a working piece of code, you want to look at something like that and say, how do I attack that? How do I turn that into something that I could possibly code? So here's the equation here. How could I turn that into something that I could possibly code? Yeah.
You always split them up with 3 different things.
Split what up? Into what different things?
Like split the 3 different or the 3 different sections into like 3 4 loops in a thing, and then make them equals like whatever's like in an array after you.
What do you mean by that? So these 3 pieces?
Yeah,
Okay.
split them up into separate like 4 loops.
Why do they have to be separate for loops? What is the process we're doing here? Because we need to be guided by what the differential equation says, right? The structure of the differential equation tells us how to approach it numerically. So we're going to walk through how we make that approximation right now. The first one is the easiest. Oh wait, maybe not.
They ask them like what approximation? we're
Yeah.
using For time.
Forward time. Why is that? Because if I do something like this, I'm going to simplify it dramatically, okay? Let's make this approximation. How do I say W or omega at a later time? Forward time, what does that mean?
So that is how it's one.
What's that?
You're comparing future step to the previous step.
Yeah, so we're gonna know where we're headed based on something that looks like a velocity. So this per unit time looks like a velocity. And I'm taking everything on the right hand side and I'm just calling it beta, which is just a number like 70. Okay? And I'm saying if I want to know omega at a later time, the approximation is omega at a later time is equal to omega at the original time plus
Let's make it the future or data T.
beta times delta t. That is called what?
For time.
Forward time. It's also called Euler's. It's also called Galileo's equations of motion. It's also called kinematics. It works the same. And it relies on the principle that delta t is small. Okay. So that was beta. Now we have to figure out what the beta is, right? Okay, so now we have to look at all of these pieces. So I know that I can do that part. That's easy. I've done that 1,000 times. I could use RK4 if I wanted to, as long as I can calculate beta at each time step, right? So now I have to worry about this garbage. What's this garbage?
With a bunch of forward space problems.
Are these forward space problems? You want to do forward space? Let's think about the space again. So, these things I've turned into. I need like strong chalk. Okay. This is psi. Right? So now I've gotten rid of the UV, right? And I need this again. Okay. Do I need to know what rho is? No. So I need two essentially arrays. I need an array that tells me omega at every location and psi at every location. Right? Okay. Because here I have gradients in psi and gradients in omega. If I want gradients in either of these, what would I use? Yeah, center space. Almost always going to want to use center space. The easiest derivative. It makes a lot of sense. It's just like this, but it spans the space. So for example, if I have something like this, say that equals something. What? Okay. I was just gonna say we could write this in. Okay. So let's say this is omega at a location I. How do I write this? I'm mixing letters on. Now you're gonna be really upset about that.
Omega r minus 1.
Okay.
Minus omega I plus 1.
All the way around.
And then over two space times.
Finite difference. Finite. I can calculate it. Difference. Not infinitesimally small. Okay, so that's that. Is psi harder?
Okay, so it's forward space.
Forward space? Center space. Why do we want forward time and not center time? Can't look back in time. Time has a flow. Whereas at every time that I think about conceptually, your brain right now is seeing the entire room in instances of time, and all of the fluid is at a snapshot. Right? The curvature in space is very different from the curvature in time, because time flows and space doesn't. I mean, it kind of does. Okay, so how do I write this one? This one will be quick. Yes. Very good. Okay. So if I look at that on the left and on the right, I remember that I just have these equations just sitting around, right? Because these are just items, right? If I have this thing right here, this beautifully discrete box with values at every single point, where's the delta x? Right? Or right? Where's delta y? Okay. And we would be insane not to make them equal. Okay. We don't want to have some weird long grid. You can have more steps in one direction. That's perfectly okay. But don't make the y 6 times longer than the x. There's no reason for that. Right? In fact, that's bad. Why is that bad? It's not just confusing.
Hard to code.
Not just harder to code. I mean, you could just change the letters.
Okay.
You could have, let's say I have an Amazon package like this, right? Okay. You have some fluid in it moving around, some long tube. That makes sense, a physically long tube. Okay. But if I have my bin sizes 6 times longer in one direction than the other, what issue does that begin to present?
You're not gonna get like the details in that direction.
Correct. This is a finite difference. So therefore, the differences are worse in one direction than the other. Right? These are approximations. This is not really an equal sign, and it kind of looks like an equal sign, but it's not. So in fact, in this location, this delta x means 6 times larger, means it's probably at least 6 times worse. Okay. I can add more points. I don't mind. Right? Go up and down, have a really long box, have 10,000 points in this direction and 100 this way, but the grid spacing has to be regular. It also matters because if you imagine, if I took my box like this and I rotate it like this, okay, and that grid spacing that you had before, where one is 6 times longer than the other, do you think you'd get the same picture? No. And it should not depend on your orientation, right? Physics doesn't depend, for the most part, on how you view it, right? Okay, so we did these first 2 parts. This one, that was an easy one. These ones, is this going to be harder? No, it's the same. Same, but different, right? Okay, what's this stuff?
Three points.
What's that?
3 points for the approximation.
Yeah. Need 3 points for the approximation. But this one is, if we recall from our computational, this is going to give us more tricky, more difficult. Why? Yes, and what's that now? What do you mean by split it? So we don't want to decouple it. In fact, in the Poisson equation, if you think about it conceptually, if I place a charge down, right, this sets the distribution in the entire box. Here's charge here. Now I know where the potential field lines are everywhere. So we had an example in computational where we put 2 boxes like this. Okay. And we let without anything changing, we asked what's the distribution. There was a positive here and a negative here. And we said, without anything changing, without new particles were being introduced, I'm just going to let this flow, and the boundary conditions will tell me what the answer is, right? You had something like this. I forget what it is. Imagine that that's right. I think it's backwards. Some garbage on the right hand side. Okay? So this is the Poisson equation that we know and love. We know how to solve this. Because as long as we have whatever's inside, we can find the correct solution. Okay? Remember that? What is that process called? How do you solve this equation? What we're going to do in yes, we're going to look at all the steps around it. So that's it in practice. Right? This point here is going to depend on these points. But what is the name of this technique? The relaxation technique. Why is it the relaxation technique? We're going to use awful analogies again. Imagine that this is a box or a bowl, okay? And I have some like wonderful pizza dough that I'm gonna make, and this is a weird square pizza that I'm gonna make, and I toss my pizza dough in, and for some reason my pan has like a keys here, and like a hole in the pizza dough. Okay. So there's, yeah, my keys. I left my keys in the keys. So, yeah, okay. So I throw the dough down. And now I look, and the dough is draped over the keys and is falling through the hole. The dough started off completely flat. And as it moved down, right, as it was falling in time, it starts to map the outline so that the surface tension gives it exactly the shape that it can take. Doesn't immediately cut, doesn't bunch up in other places. It's fully parameterized by what's actually inside. Specifically, these second order differentials in space. So the curvature of what's inside the space tells us what the solution is. Does that make sense? I know that's a horrible analogy. I just came up with it. Assuming that, okay? Okay, so this part here looks like yeah, there's a lot. Ignore this now. Oh, we're only looking at this thing. The diffusion part. That's correct. So all of this garbage over here, we can move that over. Or we can do what we said over here. We called it beta. So let's write it over here. I have the diffusion of the vorticity. And let's call it alpha. Okay, fish. We'll fish emoji. Okay. So this piece here equals all of that stuff on the left-hand side. And if you want, you can divide by new. I don't care. So now I've begun to understand how to do this at every step. Okay. The very first thing I have to do is I have to solve for the vorticity. Because the vorticity is going to tell me at every single step everything else about the fluid. Okay. So here I solve this piece with what's that?
Relaxation.
The relaxation technique. Okay, so I solve this with relaxation. So I'll need one piece of code to do this at every time step to solve the relaxation. Now that I have the vorticity at every location, these are quite straightforward to calculate. Right? Right? These are just numbers. We said that over there. Just differences between nearest neighbors. Okay, so now I take the differences, I add them all up, and I get beta. And I just move your steps forward. Did that make sense conceptually? Who's left out in the dark? Raise your hand. Okay, what part did you like? Want me to do it again? Okay, so we're going to start over here because the Poisson equation at every moment needs to be satisfied. And this is the most difficult part because while these are combinations of nearest neighbors, this requires on all of the information to be consistent in the entire domain. Okay, so the curvature like this, right? If I update it here, if I make little changes, that will propagate all the way to the other side. Right? So if I look over there, I introduce a key or I introduce a hole into my pan, and that's going to change the shape locally, but also it'll change the shape far away by a little bit. You won't notice it, but there'll be some downward curvature at the edge of the pan, right? Because the whole thing is one giant fluid that's touching. Okay, so at the very beginning of every step, okay, it's March 1st, I calculate the shape of my pan. And then based on the shape of my pan, I know how the dough should be oriented. Okay, once I've done that, I can just look at the solution and I can calculate these bad boys, right? And I know that this one here, psi, is related to omega. So I'm chilling, right? Okay, and then finally, I say, oh, I want to know what it's going to look like tomorrow, and I just propagate it to the next day. So I have three separate actions. Okay, I have a time loop, I have a Poisson loop, and I have a propagation. Poisson, yeah. Poisson, like croissant, but not spelled at all the same and not the same words. Okay, same but different. Okay, you want to see it?
Yeah.
So quick. um Hold on, this got backwards.
The time propagation and then this one loop.
Yeah, and I'll show you those different pieces right here. This is my baseball. You don't want that. Where did my thing go? Here we go. Okay. So do not worry about copying or taking photos of this here. Where is my code? Is it launched? Everyone's working in this, right? Mostly? Okay. I just started working with a new friend from Spain, and like it's always tenuous. You start a new collaboration and you're like, they're gonna be cool, they're gonna be weirdo, right? And so he was like, oh, let me send you some code. I'm like, oh, it's good code. And he's like, it's in IPython notebooks. Yes, let's go. That's all I write in. Okay, so here's the solutions to the fluid problems. We'll post these. Because what is the important part of this class? Learning learns, right? Okay. And of course, there's always problems with my code. I do that intentionally. Because if you just read someone else's code, you haven't learned anything. And if you just read from ChatGPT's code, you've learned less. Why? Because if I hand you code, I can talk you through it. ChatGPT does not know what it's doing. It has no self-actualization. It does not know what it's written. It is only telling you what it thinks should come next. It's a tool, highly flawed tool. It's great if you want to start a marketing business. It's great if you want to write a letter of recommendation for one of the 30 that you've gotten, okay? It's not great. It's not great for code, and I'll show you why. Okay, so, oh, that's so funny that's written in there. I wrote that. Okay, so I just grabbed this, right? So here we have some problem parameters. I didn't do this properly because they're not separated, but I don't care because you're going to do it properly on your own, right? In general, you want to think of this section of the class. We're going to move away from computation, but I'm going to keep, as you see new things, I'm going to have you code it instead of having you do derivations. I think derivations are stupid. Math, does anyone think math was discovered? Okay, does anyone think math was constructed? Has anyone not thought about it long enough? Okay, you're gonna have a late night sesh. Really think about that because it'll fuck with you. So we're gonna use it as a tool in this classroom. And I think that there's two different ways to use math. You can start at the first principles and work down, right? And that's like brilliance, right? You can start at the answer and work up. And you can meet in the middle, right? A lot of people meet in the middle. You know where you're supposed to go. You know what it's supposed to look like. You work backwards. How do I adapt the code that I have to make it do the thing that I want instead of just writing brand new code every single time? That would be insane. I copy and paste large section of my code all the time, and I don't know what they do anymore because they started 6 years ago, right? Okay, that's why we put comments. So look at this section here. You have things like importing. You have all of this stuff here. I have a weird word. Ah, viscosity, that's a great one, right? Okay. dt, time step, time, initial time. Okay, max it, how many times is gonna do what? Interesting. Iterations, specifically iterations, and I'll show you why. Beta? No, actually not. I shouldn't have written that there. That would be funny if I did that, but I'm not that smart. This one?
Also,
How wrong I can be in which step? No. No.
before putting it into the.
The Poisson loop. Okay, remember that in the Poisson loop here, this is the most important part. Okay, I have some boxy box. How close am I getting? Is it like pixelated blocks like this, or is it smooth? Right? Okay. So this section here, beta, max it, and max air, those are all going to come with us. Max step, that's coming with us too. And those are all going to come down here. I make some arrays. Really great array names. You're gonna love this one. Stream function. Yeah, not San Francisco, because we don't rep San Francisco. VT. 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 Vorticity. Yeah, sounds right, right? VTO. Old vorticity. I like it, but it's vorticity initials, correct? But it's vorticity old in this context. Nothing special. This one here, ooh, it's scary. Step sizes. Which direction? Huh? Why are you saying X? Why are they equal? Because they need to be. Okay, I told you at the beginning they need to be equal. If you look up here, these are different, but this is the number of steps, not the size of the step. I do not care whether this says NX or NY, except for it's going to tell me how many steps I have. Right? This is the width. This is the number of steps. Therefore, this is the step size between them. Okay. Now, this part, really important. You just set up the arrays so they're not garbage, right? Okay. Then let's look at this part. Here's my vorticity field. I need to start with an initial vorticity. If I start with nothing in there, the computer gets really upset. It's just not very happy. Because you have some requirements that vorticity, for example, is closed looped in this other garbage, right? So it's got to maintain that. So you give it a smooth function, whatever, you let it go. Okay, this is the main time loop. This is where all the magic happens. The first part here, I step and max I step range. Okay. And this is telling me how long I'm going to run it for. Let's say 200 time steps. Each of my time steps is a specific distance. You can do this any number of ways. You can do 4t in 0 to 20 seconds. I don't care. Right? Whatever way you want to do it. You can copy this. I don't care. This part here is the part that matters. Okay, this is the stream function using what is OR? What is R? Relaxation. Relaxation, good. OR? Over relaxation. What we're going to do next week, over relax, and then it's simple, but that's okay. Super. Okay, actually, from now on, it's super. Okay, it's super over relaxed. Okay, so in this process here, we're going to do a couple different things. We're going to walk through this process, and here you essentially are going to be creating the stream functions, which are just going to be the beta, which is your overclocking parameter from Gauss-Seidel. Remember that? Yeah, where you crank it up rather than it just being equal to, like, you imagine this process here, and this is your velocity. You could just fake it, and you could say, well, I know I'm heading in the right direction, but I'm going too slowly. So I'm going to add here a number that's like It's whatever you want, so I pick 1.5. I want you to go 1.5 times faster than you're supposed to. That's over relaxation. Right? Not just relaxing, you're speeding it along. Okay, so that's your beta parameter. And then you have these different pieces of the stream function in here. Okay. And some stuff about the vorticity. Okay. I think we wrote it up here. This is what you're solving, right? Okay. Okay. So you solve the stream function. You look for the largest source of error between the original and the stream function that you have now. And if the error is smaller every single place, you're done. Okay. And then you say, okay, my old vorticity is now my new vorticity. I solved for the vorticity and I'm very smart now. Thank you. And now I go through the process and here is VT, the new vorticity, is equal to the old vorticity. Remember that in computational, we don't care if it's on the left-hand side or the right-hand side. Just gonna let it go. DT, so that's this piece right there, okay, in the real way that we're using it, and beta. So all of that garbage is my beta. Okay, you see everything on the right-hand side is my beta. And it's just, look at how long it goes. It's just differentials, but it's nearby differentials. And you have to be careful, okay? You write it down and you're careful with your little letters. I always say, write it down on paper first, because you'll see on paper a lot better than you'll miss all of my, what are they called? Parentheses and square brackets and whatever other garbage, okay? And then you do the parameters on the side. You don't update them. And you're done. Soupity doop, right? Scoop-de poop. And then you plot it. Here's how I got the U and the V. I told you it was broken before. And there's the code. Any questions? Okay, I'll post this code today. You can play with it. Figure out what's wrong with it. Change it, amend it. If you hand it back to me, I'm going to do this. Okay? You just change all the variables. I'm like, okay. All right. On Wednesday, you'll notice that in the slides today, there's no new content. So in the slides for Wednesday, we'll be talking about ideal flows for the first time. Give me homework if you have it.